Okay, I've got a torch, I have an A1, an A2, an A2L, and an A3. You wanna go see what they actually look like under fire? Oh yeah. Did you know that all refrigerants are actually flammable? Maybe not as flammable as you would think. You know, a lot of times you and I think of flammability as either it lights, it ignites, or it doesn't, right? Well, that's really not the case. We know from the combustion triangle that we have to have three important things. We have to have fuel, we have to have oxygen, and we have to have our ignition source. Well, how much fuel, how much oxygen, how much ignition, and at what pressure, right? There are a lot of variables out there. So we're going to talk about the different flammabilities of refrigerants to have a better understanding of how this all looks when we're out into the field, out in the industry. So ASHRAE sets the standard for all of our refrigerants. We basically have two letters, A and B, and four numbers, 1, 2, 2L, and 3. So the AB, that's for our toxicity. 1 is no flame propagation. 2, 2L, and then 3, right? 3 being highly flammable with lots of propagation. There's actually a lot of different scenarios in between, but we're basically going to look at 4 primary classifications, all built from ASHRAE. So all the refrigerants that we currently know, as well as all the refrigerants that could be coming in the future, will all be based on that application. Well, what does it look like though, right? To you and me. Now we have wonderful friends in the industry from like Chemours and even Honeywell who shows us in a lab what that looks like. And we've seen YouTube videos of people, shooting flames out of different things, being able to kind of look at that. But we have to remember, all refrigerants, classified refrigerants, are regulated by Section 608 of the Clean Air Act. That's what our Section 608 license is for, right? To make sure that we don't knowingly release refrigerants. So that is our regulated refrigerants. But did you know that other industries are also going through the exact same phase down? Did you even know that other industries use the same chemicals that we do? One very popular one is the aerosol and the foam blowing applications. They've went through all of these phase downs and phase outs that we've seen over history. I mean, we used to use CFC-12 for refrigerant. Well, the aerosol industry used CFC-12 as a propellant for insecticides. We've used R-22, we've used a variety of different refrigerants as propellants and aerosols over time. So other industries are going through this HFC phase down that started in January 1st of 2022, if you didn't know that. So the Kigali Amendment to the Montreal Protocol established the phase down of HFC refrigerants. We started with a 10% reduction of all HFCs January of 2022 by 10%. Anybody see the price of refrigerants go up last year? Yeah, absolutely. And I would say a pretty decent amount of that is because of our HFC phase down. I hope you're aware that January 1st of 2024, we're actually going to add a 30% reduction to those HFCs based on global warming potential. So a lot of our refrigerants are on this slide and they will be going away in the very near future. Some of the refrigerants that you know very well and very comfortably right now. So we have to get comfortable with all of this transition. We will have reduced those HFC refrigerants by 85%, which means they will almost be gone. So we have a variety of new refrigerants, and a typical balance to look at is the higher the global warming potential, the less the flammability. So as our global warming potential is coming down, our flammability is going up. But remember, what does that look like? And what does that look like to us in the field? Well, we are restricted from knowingly releasing regulated refrigerants, but what about those other industries? Huh? All right, that's a little bit of a loophole for us to do some testing and to understand what these HFC refrigerants look like. Actually, a variety of different refrigerants, not just HFCs, but HFOs and our HC refrigerants. So we've got a few of them to work with here, right? So we're gonna do some experimenting to get an understanding of what these look like in the field. We're going to take a look at tetrafluoroethane. Any ideas what this might look like? In the world of refrigerants, this would actually be 134A. But since it's used in an aerosol, it is not a regulated refrigerant in this application. Okay? We also have, this one might not be as familiar to you, difluoroethane. This would actually be R152A. You're probably not very familiar with that, but this is an A2. Remember, our 134A was an A1. This is an A2, so it is a mildly flammable refrigerant. We've actually looked at using this in automotive air conditioning and it didn't really happen. But now we have it that we can experiment with. Here's one that really is going to be fun to play with. All right, so this one is tetrafluoropropene. Any ideas? This is actually 1234YF, our newer HFO refrigerant. Now, what is an HFO? You want to know? An HFO is kind of an HFC in disguise. What I mean by that is when we look at the composition of our molecule of an HFC chemical, we have carbon atoms at the core, and then we have hydrogen, and we have fluorine, hydrofluorocarbon, right? Now, depending on how many atoms we have of each one will depend on the actual chemical name and state. And it also changes the stability of the chemical, especially when we're going from a liquid to a gas state. That really has effect on the strength of the bonds within our entire molecule. Well, we needed to get to a lower global warming potential refrigerant. So scientists at the Chemours company were able to modify the bonds and use in chemistry what is known as an alkene or olefin bond between our carbon atoms. So it changes the strength and the structure of those. Now, we do still have hydrogen and we do still have fluorine, so we have a hydrofluorocarbon. It is just bonded with an olefin bond, which means it doesn't have the same stability as it changes states from liquid to gas in the atmosphere, right? Keeping it confined within a refrigeration system, it's just going back and forth like all other chemicals. If it happens to get into the atmosphere, our bond is not going to be as strong. The covalent bond is not going to hold together as well. It's going to break apart and it is going to dissolve in the atmosphere, which is why we have such a lower global warming potential. This gas doesn't stay in the atmosphere the way our previous HFCs did. So that is the design of your HFO. It still is using hydrogen, fluorine, and carbon. It's just done in a very different way. Has a very low global warming potential, and we're going to see a lot more of that. And then we have our A3. Now this is actually propane, so it's got things like sulfur dioxide and it has different odorants in it, has impurities in it. If this was completely purified into its cleanest form, we would recognize this as R290. It's just propane, right? Hydrocarbon, A3, highly flammable. So we have all four classifications, A1, A2, A2L, A3, and we're going to go see what they actually look like in real world scenarios that you might encounter out in the field. Now, the thing to think about with refrigerants is that we're talking about the stability of a chemical. So the place that you're going to experience ignition the most is when we change state, right? When we change state from a liquid to a vapor, that's when our energy is going to be expanding, our gases are going to be expanding, and you have the most potential for ignition. But in that expansion, it has to be a pretty specific combination of fuel, oxygen, and our ignition source. So, are you ready? Huh? Oh yeah. Let's go see what we can do with all four classifications of refrigerant. Okay, before it gets too dark, I wanted to show you what we're going to be using for this experiment. We have our A1, our A2, our A2L, as well as our A3 flammability chemicals. We're going to be using three different ignition sources that are going to be common to equipment that we know. A silicon carbide igniter, a silicon nitride igniter, as well as a direct spark ignition using a Honeywell ignition module. So we're going to see what we have for flammability on these four different classifications of flammable gases. All right, let's light this stuff up. So we're going to start with our 134A. It's about 80 degrees outside, so we should have about 100 psi in this can. We're going to use the trigger to adjust the velocity a little bit, and yeah, nothing lit so far. And let's move on to our 152A. Should be around 90 psia. Different velocities with the trigger. Yeah, still nothing. Okay, let's move on to our 1234YF. Should be around 104 psia. We're gonna get this sucker really hot. And yeah, still nothing. We can boil some sap out of the mahogany bit, and we can't get that 1234YF to light. What about some propane? R290, around 144. Of course, we're reducing down with our regulator, but you can see that our propane lights pretty easy, and propagation is pretty high with a highly flammable gas. Okay, what about an open flame? We'll start with our 134A again, and yeah, there's nothing going on in there. So let's move on to our 152, our A2. Yeah, actually get just a little bit of flutter in that flame. Not a lot, but we can see a little bit. How about our A2L? Yeah, almost nothing. Okay, let's invert this can and see what happens when we go from liquid to vapor. Oh, looky there, a little bit of ignition on this igniter, not on that one, and nothing on the intermittent ignition. Okay, now let's try our A2, our 152A. Holy HFCs, Batman! Look at that flame. That is with an A2 as it's converting from liquid to vapor, and not so much on ignition. And the moment we've all been waiting for, our A2L. And not really a whole lot. More like an A1. There's a little bit of flutter, but absolutely nothing on our electronic ignition. Oh, if I get it just right. And super, super hot ignition. Okay, let's see what happens with a direct flame. So our 134A, yeah, I mean, there's a little bit in there. Not a lot, but a little bit. As we increase our velocity, our propagation actually goes down. Well, what about our 152? Yeah, that's a lot of flammability. That was our A2. Let's take a look at our A2L, and, well, yeah, there's a little bit. So a little bit more than an A1, but definitely not as much as an A2.
So what does all this mean? Well, it really means that all refrigerants really are flammable. It just depends on the amount of fuel, the amount of oxygen, and the energy, and the amount of that energy that is in our ignition source. So when we look at our refrigerants, we need to understand that even our A1 refrigerants, this 134A, did ignite when it was in the right circumstance. It had to be changing state from liquid to vapor. All of our refrigerants here are showing examples of propagation when they're changing state from liquid to vapor in an open flame ignition source. Now, we didn't see those similar effects when we're talking about vapor, and we didn't see as much of it when we're talking about liquid in lower ignition sources, like our hot surface igniter and with our direct spark ignition. Very different ignition scenarios. So just be aware that all of our refrigerants have some type of flammability to them. Our A2L actually is much closer to an A1 than it is like the A2, and definitely nowhere near the A3. It doesn't have a lot of flame to it. And if you notice, when we start applying more pressure, more velocity to the refrigerant itself, our flame propagation actually diminished. So the window's very, very small. So a lot closer. I would actually rather seen this A2L down here close to our A1 and our A2 up here really close to our A3. But that's just the scenario that I see. So thanks for joining us. If you want to use any of this footage, please do. No need to duplicate it. You know, we took a lot of extra safety precautions to make sure that we had a proper atmosphere to do this testing. We're on concrete. We have all highly flame resistant clothing, fire extinguisher, and it's just a great opportunity for us to experiment with the true flammability of these refrigerants in real world scenarios. Have a good day.